We'll begin the class, as we always do, in 1920s Poland. Now, the Polish intelligence officers have been listening to signals, and they've intercepted some Morse code signals sent in international Morse code by the German military. Now, these are all well-formed letters, and when they decode it into letters, they find what looks like a standard radio message, except that the body of the message appears to be gibberish. Well, now they're used to the idea of encryption, so they set about trying to decrypt it. But they're not able to. This has become a real challenge. This is something new. So let's take a brief detour and talk about cryptography. If I want to send a message out, a secret message like the duck wants grapes, I might do something to hide the message. Maybe I'll seal it up in an envelope and send it with a pack of cigars on horseback. But that's proven to be an unreliable method in some cases. So maybe what I'll do is I'll encrypt the message. Now, encryption basically scatters information. It takes some of the information out of the message and puts it in a key, and some of the information out of the message and puts it in a mechanism used to encrypt it. So if I get the message, if I intercept the ciphertext, the encrypted message, I don't have all the information I need to understand it. Right? I need to know the mechanism, by what means was it encrypted, and I need to know the key. And when I have all the information together, presumably, I can then read the message. But until then, I can't. So I want to send the message, and I want to keep the mechanism, perhaps, and the key, certainly, secret. Through custom seizures and other back-channel intelligence methods, they're able to get a couple of these machines, these devices enclosed in a wooden box. They're battery-powered, and over on the right, you see one of these, an Enigma 1 in this case. And it consists of a keyboard, a set of lights just behind the keyboard, a set of 3 dials behind that, and a plug board on the front. Okay? They notice that when you turn the machine on, and you push one of the keys down, a light turns on. But it's never the same light as the key you press. So, for example, you might press F, and U turns on. You press F again, and K turns on. You press F a third time, and M turns on, but it will never be F. And they can just sort of observe the behavior of the system. Every time they push a key, one of those dials in the back, the rotors, advances one position. And once it's advanced so far, the second one advances. And once those two have advanced enough times, the third one advances. So every time you push a key down, a mechanism inside the device advances the rotors. So that's kind of curious. So it's clear that some combination of the key you press and the position of those rotors has something to do with which light lights up. In addition, on the front of the device is a plug board. And so you can look at that and see that it's possible to connect one letter to another. But that doesn't tell you the whole story, right? I might push down a key. Let's say I push down F, and on the front I've connected F to M, but M isn't what lights up. So that's interesting. That tells me that there's an additional mechanism inside it, probably related to those rotors, that I need to figure out. So let's open it up and see what we find inside. So here's a schematic of basically the device itself. I'm going to go through it in little pieces here. So when I push a key down, indicated by that red arrow, I make a connection from the battery over on the right to the rest of the machine over on the left, and I break the connection to the bulb above it. So I'm pushing down the key for Q. That breaks the connection to the bulb for Q. So one thing I can learn from just this little bit of it is that when I push a key, I can never turn on the light that corresponds directly to that key. So pressing Q will never light the Q light, since it simply can't. So there you go. Now, we've already pointed out that every time you push a key, the rotors advance. And we know that about every 26 times of the first one, we get an advance of the second one. and about every 26 times of that, we get an advance of the third one. So does it advance when you hit Z? Well, not always. Sometimes when you hit M, it advances, but it's consistent. So that means that somehow maybe you can change the letter on which it advances the next one. All things to think about. So let's trace the signal through the machine and see what happens. So I push the key down, and I go into this plug board. And so, for example, I push Q, and then the plug board, let's say I don't have anything plugged in for Q, then Q just maps to itself and passes straight through, out the back. Okay, that's fine. If I connected it Q to F, then F would be the signal that came out the back. All right, fine. They're just electrical signals. That signal then goes into the set of rotors. And each rotor has a set of contacts on either side. And you can see those, right? So I have these little contacts, and if the rotor is aligned correctly, there's a physical mechanism that forces it to align correctly. These contacts, these make a connection, and power can flow through them. And inside each rotor is a series of wires that permute the inputs to the outputs. Now, they don't open the rotors up, but they're able to figure out what happens by applying current to one side of the rotor and observing where that current appears on the other side. So they're able to work out what those permutations are by observing the behavior. All right? So they poke at the rotor and they observe how it pokes back. Right? That's what is the behavior when I do this? That's essentially dynamic analysis or an experiment. And the experiment says what happens when I apply current here, and I observe where the current comes out. And it's consistent, so I can infer that there's a wiring inside the rotor that permutes the inputs to the outputs. Great. So I know that about all three of the rotors, and I can look at the mechanism with the device open and see that there is a little piece on each rotor that when it comes around will catch and advance the next rotor. Great. And that can be moved. So that's another thing I can change. Once the signal makes its way through the rotors, and they could be rearranged. They can be taken out and rearranged. And if there are three, then that's 3 times 2 times 1, or 6 different combinations of them. Once I go through there, I go through what's called the reflector. The reflector permutes and reflects the output from the rotors back into the rotor stack. That's a fancy way of saying it just makes a connection from each of the outputs of the last rotor back to an input to that rotor. Now, it's important to think about this for just a moment. I can't connect that output back to the same point because current can't flow both directions along the same line. So I have to connect it to a different line. And that's true throughout, right? Once I've connected to a different one, I follow a different path back through them. And a consequence of that, if you think about it for a moment, is that I can't flow, when I push the Q key, I can't flow back to that same spot and light the Q lamp. I already know I can't because the connection is broken, but I further can't because I can't flow back along that same line, and that's the line I need in order to illuminate Q. So I flow back along a different line where the key is not pressed, and that allows it to flow to the lamp and back to the battery, completing the circuit. So there you go, right? Signal travels back through those rotors. Each one permutes the signal again back to the plug board, which might permute it in a different way, and in the little diagram here it does. And so all along the way I have these possible different permutations of it. I've pushed Q, it goes to the plug board, each of the 3 rotors, through the reflector, back through the 3 rotors, and back through the plug board, and then illuminates a lamp. Wow, that's quite a bit. And the encrypted letter that I get out of it is what I write down. A couple things to notice. It's deterministic, right? When I set the rotors to a certain position and I push a key, I get a certain output. Now, the rotors advance, and where that little tang is that grabs and advances the next rotor, that changes how it advances. So I might push Q and get E with the rotors in a particular position, but based on how I've set those little rings that have the little tang on them, I might get a different result for the next because it might advance one of the rotors or it might not. So there's lots of settings in this machine that control how this sequence works. Another thing to notice at this point, and this is an important point here, is that it is symmetric. The encryption is symmetric. Why is that? Well, suppose I push Q and it shows me E because of this convoluted path to the machine. Now, stop for a minute and presume that, no changes, suppose instead of pressing Q, I had pressed E. That's going to map to exactly the same path to the machine with all the arrows reversed, and I will illuminate the Q bulb. The encryption's symmetric. So that's an important realization. Those are important realizations. That means to encrypt a message, I set the rotors and the rings, I maybe set the plug board, I press in the keys, and I can get the encrypted message. But if someone started with a machine in exactly the same situation I had it, and they typed in the encrypted message, they would be able to read out the clear text message. So the thing I don't know, but need to know, is the precise initial settings of the machine in order to be able to read the encrypted messages. That's important information, and the Polish people figured that out. So how does it work? Well, there's a really good video on YouTube that explores the machine using 3D models of it. It's a little slow, but it's fun, and I think you might enjoy watching it. It sort of shows you how the plug board works, how each of the rotors works, how the reflector works, all of that. And I think you might like that. But for now, let's go back over sending a message. The German military had a key sheet, and that key sheet specified the rotor order, right? Which order do I put the rotors in the machine? The ring settings, right? When does it grab the next rotor and move it? The plug board connections, and the initial positions of each of the rotors. So once I look at this key sheet, and it tells me how to set the machine up. And once I've done that, okay, great. Then I'm ready to do this. And everyone has this same key sheet, so they can then set the machine up in the correct position. But what if you grab one of these? What if somehow I'm able to intercept one of these, and I have one of these key sheets? Well, that could be bad. So in addition, an operator picks a 3-character key. For example, they might pick XKV. And they can pick whatever key they want. And they set the machine up in the initial position, and then they type that key twice. XKV, XKV. And they read out the bulbs that light up. And so for XKV, XKV, they might get FGKKTS. So the operator then says, great, that's the encrypted key. They then change the rotor positions to the key KTS for the 3 rotors. And now they type in the message. So the message has actually been encrypted by a arbitrary secret key. It's not on the key sheet. But then I send that message in International Morse code. But I start out the message with the encrypted key, FGKKTS. And because other operators know that, they're able to read the message. They set the machine up in the initial position according to the key sheet. They type in that key, FGKKTS, and because it's a symmetric cipher, they read out XKV, XKV. Now they know XKV is the correct setting for the rotors to read the message, so they change the rotor positions to XKV and decrypt the message. So there's a sender call sign, D or from, a recipient call sign, the time the message is sent, 1625 or 4:25 p.m. for our American friends, the length of the message in characters, and then the key encrypted twice using the daily settings. If we knew the daily settings, you could figure out what the key was. But without knowing the daily settings, that doesn't help you that much. That's followed by the ciphertext. So let's go back to our little model of encryption, and let's apply it to the Enigma. So the Polish cryptographers, they've got the mechanism. They've got the ciphertext. But the key is encrypted using these daily settings that they don't have. So we could think of the daily settings maybe as part of the key. Information is missing. That's kind of the point. There's information that they don't have. However, some very smart cryptographers began to figure out that there are weaknesses in this encryption. One of the weaknesses is a letter never encrypts to itself. So when I see a long message, I know immediately some of the letters that can't be there. I know that they can't be those letters, right? And next, I know the key was encrypted twice. And that tells me something very powerful. It tells me that for the encrypted message, the first and third characters must decrypt to the same character. The second and fourth and the fifth and sixth, they must decrypt to the same characters, the key repeated twice. So that's pretty neat. And I know the encryption is symmetric. The same system is used for both encryption and decryption. All stuff they figured out through a combination of observing the behavior of the machine when they poked at it, how did it poke back, and opening it up and studying its mechanism. All right? So behavioral analysis, we could call that dynamic analysis because things are happening. And static analysis, we can call studying the way the circuits are put together in the machine as static analysis. How is this thing put together? Through a combination of dynamic and static analysis, they figured all of this out about the machine. Can they read the messages now? Well, yeah, they can. They analyze it as a permutation engine. There's a plugboard permutation, a rotor stack, a reflector permutation, rotor stepping updates. All these things make it hard to figure out what the message is, but it means they know how the machine works, and they could build a stack of them, and they could cause it to mechanically run through a lot of different key variations, right? You turn it on, and it spins through all the different possible key combinations, about 26 times 26 times 26 key combinations. It also means you got to know what the ring combinations are when you advance the rotors. All those things are things you've got to figure out, plugboard position, all of that. But it's still a finite number of things, and we know something. We can quickly throw away certain information, right? As soon as I put in the encrypted key and I don't get a match on those characters, I can throw that system away. And in fact, I could build it so that it advanced on the first entry, it advanced to the position for the third entry and quickly check if those two match. I don't have to enter all of those. I can just try those two. And whenever they do match, I have a candidate for the first character of the key. And then I can look for a candidate for the second and a candidate for the third. And when I find all of those, I can try that and see if it works. So I can mechanize this procedure. And they do. They build a machine. They call it a bomb. Strangely, no one quite knows why they called it that. There are theories about it, and you can go read on Wikipedia about the different theories, but that's what they call it. And this allowed them to rapidly test configurations. Okay, and once they find the one that yields the right result, then they know it. Now, the Germans figure out that this is going on, so they add rotors and they make some changes. And ultimately, this leads to the whole effort at Bletchley Park. You can watch a movie about it. That's all good. But all this early work to figure out Enigma and how it worked was done by these brilliant Polish cryptographers. Now, Polish cryptography falls on hard times for reasons. Poland is invaded by Germany, which sets back the Polish cryptography efforts. England is never invaded by Germany, and so you can continue the efforts up there. But I don't want to forget about these folks who did really the heavy lifting to get the whole decryption of the Enigma started. And that's an example of reverse engineering, of both static and dynamic analysis of a human-constructed system to answer a question, to figure out what it does. So let's talk about the class a bit. So the goal here is for you to develop the ability to reverse engineer binaries, compile software. And we want you to combine a architectural understanding. What is the machine? How does the machine work? With program analysis techniques. Right? What is this particular program doing? And among those are, what's the control flow? What's the data flow? What are various semantic properties? And we'll do that, and we can assume that it's just an ordinary piece of software with no malicious intent, or we can assume that it's a piece of software that someone has written in an effort to try to cloak what it does. And we'll look at combinations of all of this. The outcomes that you should want from this class: be able to analyze a compiled binary program without source code. If that's something you want to do, this is the class for you. Recover program structure from raw machine code. Apply automated program analysis techniques. That can be good by itself. There's a lot of things that you can apply these techniques to, just a lot of challenges that you can solve in software. Compilation, optimization, just program analysis. All of those are things that you can do, not necessarily have to be reverse engineering. And interpret and evaluate compiler and linker artifacts. We'll look at lots of different pieces along the way. Recognize and counter anti-analysis and obfuscation techniques. We will skim the surfaces. We won't go too deeply into this because we don't have time. But we will look at some anti-disassembly and how to get around that. Assess the strengths and limitations of reverse engineering tools. All these tools have limitations. They will fail in certain cases. And the way to get around that is to apply your human reasoning about how the tool works and what the problem is to figure out how to solve that challenge. Design and implement small analysis components. You'll write a lot of code in Python to analyze programs. And reason about security relevant properties of software. And we'll look at some of those as well. Operate effectively under incomplete, ambiguous, or adversarial conditions. And communicate reverse engineering findings clearly and, I hope, professionally. What are expectations for this class? What do I expect you to do? Well, I have expectations for you. I expect that you'll come to class, could be online, could be in class itself, that you'll read the assigned reading material, you'll do the homework, you'll email me with questions, and when I inevitably don't respond to your email, you'll feel free to text me. You can text me anytime, day or night, doesn't matter. I will never be mad that you texted me or emailed me. If I don't want to talk to you right then, I just won't. Easy. What do I expect you to know? See, here's something good. I expect you to come to this class knowing C11. Know how to program in C. If you don't know how to program in C, you're going to be in trouble. So if you're not up on your C, you should spend some time going back over that. Python. We're going to write these programs in Python. I'll try to give you a little bit of information whenever we get to that part, but there's not a class that's going to teach you Python. Python is not a terribly hard language to learn, and you should go and spend some time learning Python if you are not familiar with it. Linux shell interaction. Again, this is not a class on how to interact with the Linux shell. If you've never interacted with Linux, you need to go spend a little bit of time doing that. I'll expect you to know a little bit of computing theory, not anything too deep. I'm not going to ask you to state and prove 3SAT or anything like that. But you should know what a Turing machine is. You might want to know a little complexity theory. If I tell you something is linear or quadratic, or it's order n cubed, you should have a sense of what that means in terms of the complexity of the program. For basic discrete math, right? What are the logical connectives, and, or, not, NAND, exclusive, or? You really need to know those because those are going to show up a lot in assembly programs. Functions, what is a function? What is a relation? What are the quantifiers like for all and for each? Or there exists. Again, I expect you to know all these things because this is the background that you need to have to study computer science. And maybe most importantly, I expect you to understand hexadecimal and binary notation. Okay? Good news. Python supports both. You can write numbers in hexadecimal and binary. You can display numbers in hexadecimal and binary. Play a little bit with those in Python and be sure that you understand it and understand the connection between hexadecimal and binary. Hexadecimal is base 16 and binary is base 2. So 16 is a power of 2. So each hexadecimal digit corresponds to 4 binary bits. And you should be able to make that connection pretty easily. If I see a 9 in hexadecimal, I'll realize, oh, that's 1001, right? It's 8 plus 1. So there's a strong connection there, and that's going to be really important to you. So be sure you understand that. Those are the things I want you to know coming in. I expect you to learn maybe a little more computer architecture than you've had before. Maybe not. You may have had a much deeper study of computer architecture, and that's fine. I expect you to learn the Intel dialect of the AMD 64 ISA. What does all that mean? I expect you to learn assembly language. And I expect you to learn assembly language for the AMD 64 or x86 64, the 64-bit x86. But I also expect you to learn a little assembly for what we would call the ARM architecture 64-bit. Now, here's where things get a little tricky. You may have done some 32-bit programming on the x86. I'm going to tell you now, 64-bit programming on the x86 is quite different. It's going to look fairly familiar, but it's going to be different in a lot of important ways. The same thing is true if you've done ARM v7. If you've done ARM v7 or earlier or Thumb, you're going to find the 64-bit ARM architecture is different. It's going to be just different. For one thing, the program counter in ARM is completely hidden from you. You no longer reference it or use it in any way. So if you've written things where you're using PC relative addressing to get to a constant pool, you won't do that anymore. You will use the address of the current instruction as the base to reference things relatively. And we'll go over this when we get into this later on. We're going to spend most of our time in the AMD 64 world, just because, but I'll try to call back to ARM whenever possible to provide you with a little bit of a basis, and it's also good to show the differences between those two. I expect you to learn the ELF binary file structure. ELF is the binary file format used on Linux and other operating systems. It's not the one used on Windows. It's the PE file format, and we may talk about that a bit. It's not the one used on Mac, right? We may talk about it as well. Expect you to learn some security concepts that are in use in Linux. We will occasionally need to override some Linux security in order to do things like trace programs, and we'll talk about how that works. You're going to be using several tools, many different libraries for reverse engineering. We want to be sure that you know how to do that. And general program analysis techniques. I expect you to learn things like slicing and live variable analysis as we go through the class, because those are general, useful techniques. And I want you to speak up. We want a diversity of perspectives. Everyone in this class has been on some different path through life and has learned a different collection of things. You have different stuff in your brain rattling around, and it's going to connect to this class in ways that may be the same as another student or maybe different from another student. And when you see those connections, speak up, right? I think it's fine for you to interrupt me in class, unless, of course, I'm recording here, in which you can interrupt me. You can shout at the screen, but I won't hear you. But in class, I want you to speak up, right? If you've got something to add, if you've got a question, it may, adding what you want to add, that may be helpful to other folks. Asking a question is maybe a question somebody who's a little more timid has, but doesn't ask, and that's all helpful. Because I want you to interact, I do not record the classes. Okay, so you don't worry that you're being recorded. I'm not recording you. And the posted lectures are all going to be like this, where I'm recording them in my own home. I want you to try things. I want you to run the examples from the slides and play with the tools. Right? People learn by playing. So play with this stuff and see how it works. If you can get the answer to a question by hard thinking, I think that's maybe a little less useful than learning to use one of these tools or to write some code to give you that solution. All right? So play with the tools, understand how they work and what they can tell you. Understand what you can learn by writing some code and running a program. This is all stuff I want you to get from the class. All of these techniques we're going to talk about, they can be done. You can stare hard at the code and you can figure it out. But you're a computer science student. You should be writing software to make a computer do it for you. Everything is relevant. Last thing I'll leave you with, everything is relevant. You may be like, well, my background is music, or my background is history, or whatever, and that doesn't seem as relevant. It absolutely is. People come from all different sorts of backgrounds, and they bring this background knowledge to it and contribute, and that gives them a different perspective on it. And so, one thing that we know from the world is that a variety of different perspectives leads us to be more likely to solve a hard problem. I'm going to talk about why the slides are the way they are. I will skip these slides in class. If you want to skip them here, advance to time code 3913. These slides have a lot of text. That's because you don't have a textbook, and so these slides will serve as your textbook and your reference in this class. Additionally, people may have vision issues, and I've tried to be careful in how I construct these slides so they're usable for people who may have vision impairment. We'll credit all the different material that I've used. Some of this is in public domain, in which case I'll tell you. Some of it is not. It's used under fair use. I use the Columbia University Fair Use Checklist whenever that applied to decide. And for a lot of these, I've asked for permission to use the materials. I make these slides available under the Creative Commons license. Free to use them. Free to use the templates, the form, all of it. But be aware that they contain material whose copyright is owned by someone else. I've gotten permission to use it for this purpose. If you want to use that copyrighted material, you need to figure out if it's okay for you to use it or if you need to get someone else's permission. There are notes. For example, there are a lot of websites and links that appear in the slides. For those, there are notes that appear down in the speaker notes. And it's always incidental information. It's not essential to the course content. Essential course content is on the slide. Incidental information is down in the speaker notes, but it might be relevant and helpful. I have hyperlinks in these slides. They work well with assistive technologies. It's all good, but it means I can't just put the URL directly in there. And if you happen to be looking at these in not online, like in a video or something, you may want to do, where does that link go? Well, again, that's in the speaker notes in the slides, and I'll make sure you have access to the slides. And the reference number that follows it will point you to the link to that site, point to the actual URL. Why does that matter? Some people like to print these out. If you'd like to print them out and you want to have the URL, you can do that. And here's how you do it. Just follow this process, and that will let you print the slides with the little end notes down there at the bottom. If you have any trouble with any of this, let me know. These slides are full of asides where I tell you some additional material. I'm not going to expect you to learn it and know it and be tested on it. It's just information that I think is interesting that I'm going to put in the lectures, and I'll mark it with an aside. I spend a lot of time looking at fonts for some reason and looking at the research on fonts, and I've chosen fonts for this. They're different from previous classes. I've chosen Lexan for general text, Atkinson Hyperlegible for titles, and Hyperlegible Mono for code listings. If you have any trouble reading any of these, let me know. I chose these fonts because, number one, they're supposedly very good for people who happen to have dyslexia or other kinds of problems with reading, and they're open source. So these are released under the Open Font license, and as a result, I've got GitHub links to all of them down there at the bottom. You can go and get the source for these fonts and play with them, and get the fonts themselves for free. I think that's kind of useful and helpful. They all distinguish between the lowercase l, the uppercase I, the digit 1, and the uppercase O, and the digit 0. And you can see that over on the right, how hyperlegible mono does that, right? Lowercase l looks like an L, and the 0 has that little line through it. I've reduced the colors I use on the slides. There are two reasons for this. One, I've noticed that the projectors in the classroom simply don't do a good job with gray. They just wash it out and you can't see it. So I've gone in and played with them to be sure that I'm using colors that you can see. And another is I want to limit the colors that I choose because, right, I want these to be more accessible and more readable. So you'll see defining instances in dark red, bold. I don't use italics. I prefer to use bold. Italics do sometimes occur on these slides, but it's sparing because italics can be hard to see. And there's research for that, research for all of this, and you can find that at those links. I use black text, or at least dark gray text, on a white background because that is, according to the research, slightly more readable than white text on a black background. The colors chosen were not arbitrary. I spent some time using David Nichols' Coloring for Colorblindness, and the palette I chose is the one you see over there on the right, and you can see how it's affected by the most common types of color insufficiency. So if you have a problem with any of this, let me know. Please let me know. The slides are checked for accessibility concerns using Grackle. It's a tool that scans through them and lets me know when, for example, an image doesn't have alternate text, or there's a slide without a correct title, or any of these sorts of things. But if you find a problem, let me know. Grackle's not perfect. I'm not perfect. Let me know if there's a problem with these, right? And that could just be, I've written text that you can't understand. Let me know that, right? And I will explain what that means and fix it. I've syntax hinted the source code using slides code highlighter, so there'll be some other colors there. Hopefully that's still readable. I settled on the light theme, and I try to be sure that I don't go below 10-point font anywhere in these slides. I typeset math using the auto LaTeX equations plugin, and I've got all the references for this class in Zotero. And there's a Zotero group for this class where you can go and see that bibliography, and in most cases, get the actual PDFs of the documents themselves. Animation is problematic, so I tend to avoid it. Instead, when I want to reveal things in stages, I'll use multiple slides. That means if you are printing them or you're trying to understand them slide at a time, you don't have to play them and play the animation to see what's happening. That said, animation's good for some things. It's helpful for showing certain concepts, and so I haven't completely avoided it. I try to make a trade-off here. Whenever a slide has animation, there'll be the warning text animated at the bottom to indicate this. If you have a way to make these slides better, let me know. I've traded off things, colors, fonts, all kinds of prettiness, in order to get them consistent and clear and accessible. So that's what's important to me, is that you can use these. They're not super boring, but they are at least accessible to everyone. Let me know if you have a problem with any of this. Let's talk about grading. Your grade consists of 2 items. Homework that will test your ability to apply the concepts we've discussed, and exams that will test your understanding of the concepts. Homework accounts for about 60% of your grade. Initially, it will be focused on helping you learn assembly, writing assembly code. For the second half, it'll be focused on building a project. The homework assignments will all work on some particular aspect of what we're trying to do in program analysis, but they will also be cumulative. Not always directly, but they will accumulate to let you build a tool that does program analysis. So we're going to be doing that in the second half. It's cumulative. I recommend you don't fall behind on the homework. Okay? Please don't do that. Homework accounts for 60% of your grade. Take it seriously. I assign it every week. I assign it on Tuesday, and it's due the following Tuesday. I will not assign you an exam and homework at the same time. So when you have an exam, you won't have homework. The exams are a take-home. They're 1 week long. We'll cover all that in just a few moments. But you'll have homework roughly every week. It focuses on using and creating tools to analyze programs. And I want to grade your homework automatically. So please work with me by following the instructions. Just follow the instructions. I feel like it's not that hard, but it seems like it really is somehow that hard. Just follow the instructions, okay? If you can do that, that'll help me. It'll help me help you by giving you a good grade and getting your homework graded quickly. Let's do that. Now, late homework, I will accept late homework anytime up to the start of the last class. Once the last class begins, homework's closed. Your homework grade is whatever it is. But up till then, I'll accept late homework assignments. You won't get full credit for a late homework assignment turned in, but I'll accept it. The 2 lowest homework grades get dropped. So here's how they're graded. If you submit it on time, you get a point. If your solution succeeds on at least one test case, you get an additional point. And if it succeeds on all the test cases, you get 2 points. So half the credit comes from getting it to work correctly. Now, what if I turn in a correct solution late? You don't get the full 4 points. You get 3 points. Okay, but that's not nothing, right? So do the homework. I'm encouraging you to please do the homework. Exams? Well, exams are a little different, obviously. They focus on, do you understand why things work, why the techniques we're using work, and do you understand how they work? Not can you apply them necessarily, but do you understand how they work? The exams that I give you are take-home exams. You'll have about a week to do each. I say about because the exam period at the end of class is a little wonky. The one thing I really don't want you to do is give me ASCII art or try to describe something. When I tell you, give me a diagram of this, I expect you to give me a diagram of this. It's not like we live in the 19th century, right? And even then, they would give me a diagram. They'd draw it out. You can draw the diagram on paper. Please do it legibly. And you can take a photograph or scan it. Or you can use tools. There's tons of tools to let you build diagrams, but don't give me ASCII art. I don't know how much more I can emphasize that. Please don't do that. The instructions for the exam are over on the right. That's the typical instructions that I give. There you go. People like to know what exams look like. Here is an example question from the last time I taught the class. This was a question on the exam. And you can feel free to take a look at that. I don't expect you to necessarily be able to solve it right now, but that's what the questions will look like. The grading scale, pretty straightforward. 90 and above is an A. 59 and below is an F. I will round your grade up. So if you get an 89, you get a B. You get an 89.5, you get an A. All right? Hope that makes sense. Not complicated, I don't think. Schedule is over here. At the time I'm recording this, there's some stuff that's not quite been decided yet. For example, the registrar's office has not published a schedule for the final exam period yet. So I'll update that when we get close to the class, and it'll be updated in the syllabus. Class policies. Please let me know if you have a challenge to learning the material. I want to work with you to be sure that you're able to learn this and get the maximum benefit from it. I hope you're in the class because you want to know something about the topic. I don't know why you would take the class otherwise. I guess because it's offered and you need credit. That's not a great reason. So I'm hopeful that you're here because you want to learn something about this. And I want you to learn something about it. I want you to benefit from this. So if there's anything standing in the way of that, let me know. We'll find some way to try to work around it. Given all that, I expect you to be honest with me, with the other students in this class, and with yourself. And sometimes there are challenges to that, or we perceive there as being challenges to that. But I want to remind you, you're surrounded by people who've been through this process before you. I went through it. All the other instructors and teachers here went through it. Your classmates are going through it, right? We've all been in this for a while. We're going to want to help, right? We're already set up to be compassionate because we've all been through the same sorts of things, right? We're all set up so we can relate to what you're going through. Come to us and work with us before you do something that is not going to go well. I expect you to take responsibility and credit for your own work and ideas. If you know someone is going to turn in your work as theirs, I expect you to take action. That said, if you're going to use the work and ideas of others, I expect you to give credit. Now, this is something that I think is either tricky or surprising. If you went to the library and you read a paper, and that paper showed you a solution to some problem, and you're like, I can use this, I would expect you to cite that paper, because not doing that would be academically dishonest. If you are working in a little group of people, working on, for example, the homework, and it's fine for you to work in groups on the homework, I don't mind that, and someone has a fancy, clever solution to something, I expect you to give them credit. Same reason. If someone's taking your stuff and not giving you credit, that's not good. So share credit for collaborative work, give credit for the ideas of others, take responsibility for your own work, right? If you turn in someone else's work as your own and it's wrong, guess what? Right? You're going to get dinged twice. Treat others ethically, give them the same considerations that you yourself would want. All right? That's what I expect. If I think you cheated on a homework assignment, and there's no reason for that. There's just no reason. If you work with someone else on it and you're using some of their work and they're using some of your work, just give each other credit. If I think you've cheated in a homework assignment, I'll give you a 0 and I will not drop it. And I expect that you'll discuss homework assignments. That's fine. I think that's fine. If I believe you cheated on an exam question, I'll give you a 0 on that question. And it will count. Exams are a little funny, right? I take the 10 highest scoring questions and count them. But if I think you've cheated, I'll give you a 0. And I will count it. If I think you've cheated on more than one exam question, I will give you a 0 for the exam. All right? I'm not going to put up with that. And I expect you will not collaborate on examinations. I hope this is clear. Please don't test me on this. What about AI? Humans are tool-using creatures. We like to build and use tools. AI is a tool. Go ahead. Go crazy. You can free to use generative AI to complete any assignment or exam question, provided you include a statement acknowledging that you used AI. Now, this is a policy of Tennessee Tech, and you can go find it on the CITL website. It's linked at the bottom, but the statement we need is something that looks like what you see in the middle. Acknowledge using whatever generative AI tool was, maybe multiple tools, and how did you use it? I used it for brainstorming, for grammatical corrections, citations, specific sections of an assignment, or for checking my result. All those are fine. Keep in mind, AI tools hallucinate. They get stuff wrong. Okay? You, the student, are responsible for the accuracy, the correctness, and the integrity of all your submissions. Okay? There you go. I think it's enough, right? You turn in something wrong, like ChatGPT said this. I don't care. It's wrong. Okay? And you turn something in, and I'm like, why did you get this? ChatGPT. Well, you didn't credit it. So I expect you to credit it just like you would credit papers or like you would credit other students in the class. The only thing I will not expect you to explicitly credit is the course material, right? Because I expect you to be using the course material. I expect that to be where you're getting it from. So you don't have to cite the slides unless you really want to. Attendance, please attend in person if you can. I know that some of you may be at the National Lab taking this class remotely. You could be homesick. Don't come here and give us whatever you have. Stay home. So that's all fine. I don't mind you attending remotely. Attending in person is generally better because I can see you. I can see that scowl on your face and know that I'm not doing a good job explaining something and can change gears. That's helpful, okay? And you can see me. And I know you can't see me right now, but even though I'm alone in a room, I'm waving my hands and doing all the things that I would do if I were talking to the class. If you can't attend in person, attend remotely. If you can't attend at all, that's also okay. That's what these recordings are for. I don't count attendance toward your grade. So, given all of that, now we'll sort of know how the class works. Let's switch gears and let's begin our introduction to reverse engineering. So here's my definition, my view of reverse engineering. It's a process of posing and then answering questions about software artifacts. So it's a process. It's seldom a straightforward process, and it's not easily repeatable. Given the same question about the same program today and a year from now, you may go about solving it in different ways, right? Because your comfort with certain techniques, your knowledge of various techniques, and your knowledge of software will have changed. And that's okay. I'm not going to give you a specific step-by-step process to do reverse engineering because there isn't one. Okay? For a lot of reasons. One of them is it's a bit of an arms race. From the malicious point of view, it's a bit of an arms race going on. Compiler technology changes, software changes, computer processors change. Everything is changing in the world around us all the time. And so I'm not going to give you here is the specific process to use. I'm going to try to give you a bag of tools and how to apply those tools so that you can then use them to answer these questions. Two types of analysis. We talked about these when we talked about the Enigma machine. Static analysis attempts to answer questions about some artifact by studying how it's put together. If that's the Enigma machine, we open the case up and we look at where the wires run. If that's a piece of code, we might open it up and see how it fits together. Dynamic analysis attempts to answer questions by running the program and observing its behavior, or by poking a thing and seeing how it pokes back. Behavior analysis, right? For the Enigma machine, they poked the keys and saw what happened. They put current through the rotors and saw where it came out. They did this kind of analysis. Neither of these is sufficient. Neither of these is sufficient on its own. You need both. Static analysis involves reading a program and thinking about how it works. Okay, think. I look at a piece of code, I read it, and I try to figure out what it's doing. And that's useful for quantified questions, right? Is there any, right? Does there exist? And for all, those kinds of questions, those can be answered using static analysis. In fact, it's kind of the only way they can be answered. Dynamic analysis involves running a program and observing its behavior. And that's useful for specific questions that have the form, what happens when some condition, okay? You need both. What are we going to be looking at? Well, there's an array of things we can look at. We can look at high-level languages. High-level languages describe algorithms and data structures. We might look at intermediate languages, and we'll talk about those a little bit more, but they describe how an algorithm or data structure is actually going to be implemented on some hypothetical machine. We're definitely going to look at assembly language. Assembly language tells you what the machine operations are going to be. I want you to be at least familiar with machine language Machine language is a step below assembly. Assembly gets turned into machine language that schedules and initiates physical computation. Right? The machine is still a physical thing, no matter how much we pretend about virtualization. It's still, information takes up space, it consumes power, it generates heat, all those things. And that's all scheduled, or the physical computation is initiated by statements in machine language. And binary files contain the programs and the metadata necessary to run the program. So, here's a question for you. We want to know what's happening. We want to answer a question about a program. And I could look at different artifacts. And let's say that I have access to source. High-level languages are meant to be efficient ways to describe computation. Not necessarily human readable, but efficient for a person skilled in the art to construct a program. And they use abstractions, right? While loops, folds, red-black trees, bloom filters, those are all abstractions that someone skilled in the art should know how to use to construct an algorithm to solve a problem. And so you might see a statement like you see at the bottom, count index equals sum. So the indexed element of count is assigned the value sum. And we will understand that to be 0-based or 1-based. There's still a few 1-based languages out there. We'll understand that to be an offset into an array called count. We'll understand a lot about what that means. Assembly language is meant to be understandable by a human. Regardless of what you're going to think when you see it, that's why it exists. Right? Nothing executes assembly. Assembly is not something that is directly executed. Just like source code isn't. Source code is turned into assembly, but assembly existed before more complex languages like C existed. And it's closer to the machine. And it's really meant to be a human readable. It's a concession to humans. We want to be able to write specific instructions at the lowest level of the machine, but we want people to be able to read them. And so we have assembly languages. So for example, down at the bottom of that, you see that move instruction, which is taking the contents of a register called RAX and placing it at a memory location given by RDI plus whatever's in the register RCX times 8. And if you guess that that is the same as the count index equals sum, you're correct. All right? That is implementing that in terms of machine language. Now, machine code is meant to be the binary patterns that activate the circuits that perform some action. And it's bit fields, all that kind of stuff. And so that move instruction becomes what you see down there at the bottom. That's hexadecimal. Becomes the 4 bytes, 48, 89, 04, and Charlie Fox. Those 4 bytes actually cause some computation to happen on an AMD 64. Now I'm glossing over a little bit here, but that's basically what happens. So, my question is, which of these completely, fully, accurately, and specifically describes what happens on a computer? And the answer is none of them. And maybe that's surprising. But it turns out that we'll see cases where the compiler decides that I'm going to change what you wrote. I'm going to add to it, or I'm going to remove it, or I'm going to modify it for efficiency. And we'll see cases where what you write in assembly is changed by the assembler. I'm not joking. And we can also find cases where the machine code that you write doesn't necessarily run the way you think it would. And that could be because of contention among cores and scheduling. It could be pipelining. Lots of things affect how these programs actually evolve in the specific circumstances in which they find themselves. Like context matters. Even at the very lowest level, machine code, these things can happen out of order, and in some cases, they cannot happen at all. So, given those happy and cheery thoughts, how do I get set up to do this class? Well, We're going to be doing this in Ubuntu. So install Ubuntu on a computer and you're good to go. I'm slightly kidding. We're going to provide you with virtual machines on the Xerox Cyber range. So they'll be available over the network, and you'll get instructions when the course starts. But there's no reason why you can't install Ubuntu on a virtual machine or on a computer. In the past, people have tried to use the Windows subsystem for Linux to do this, and there are always some challenges. There's some places where it doesn't work quite the same way that it will work on an actual straight-up Ubuntu install. Again, because at the lowest level, you're using Windows routines as opposed to the routines from Ubuntu. So just be aware of that. So that's what you'll need. Now, what about ARM? Right? I want you to use the AMD64 Ubuntu. What about ARM? It turns out we can have the installation of Ubuntu on AMD64 also compile and run and link and assemble programs for ARM. We can do that, and we'll see how to do that. It's very hard to go the other way. I don't know of a way to go the other way easily. So we're going to stick with this approach. We're going to use two different assemblers, NASM, the net-wide assembler, and the GNU assembler. We could use the GNU assembler for both, but there are reasons why I think NASM is a better choice initially. So most of the code will be for AMD64 and will be written to target the NASM assembler. When we work with GNU assembler, we'll see some things that look different, and I'll try to call those out. So to get set up for AMD64, you will run this instruction. If you are using one of the virtual machines from the cyber range, you'll still run this instruction. We didn't set all this up for you. We expect you to do this and set the stuff up yourself. So you'll want to install Build Essential, which will get you the compilers and those tools, GDB, which gets you the debugger, CGDB, which we'll talk about later in class, and NASM. So that's good. So get all that and you'll be ready. For ARM architecture, you need to install a bunch of other stuff. Specifically, you need to install a cross-platform version of GCC, the libraries, the binary utilities, and GDB. You need to install GDB multi-arch, or multi-architecture. And then to run programs, we're going to use QEMU. And so you'll need to install that as well. You may call it QEMU. I've heard people call it all sorts of things. I'll call it QEMU because that's just what I call it. If you want to run this stuff natively, get a Raspberry Pi 4 and install Ubuntu because you'll want a 64-bit version of the ARM. If you have a Raspberry Pi 3 lying around, that's great. You can learn ARM v7. We're not doing ARM v7. So here's some C11 source. Hopefully nothing in this looks too strange to you. If it looks strange to you, go and look it up and read about it. But this is not too complicated here. I guess the language might look a little strange to you. But again, we started out talking about these Polish cryptographers, so it only makes sense to have this be our Hello World program. So there it is. You can put this in a file called hello.c, and then we can compile it. So we compile it using GCC. We run file on it. File is a utility that tells you about a file. In this case, it tells us, hey, it's an ELF. So it's an object file, a file that contains a binary program on our system, dynamically linked. It's got an interpreter. So then we can run it. And when we run it, it says what it says. What about ARM? Well, for ARM, we start out by typing AArch64, and then usually you hit tab, and you get options. And we want the GCC one. And so we're going to compile hello C to hello ARM. We run file on that, and it tells us, hey, it's an ELF again. But now it's not x86-64, it's ARM AArch64. We have a different interpreter, and when we run it using QEMU, we see the same output. Now notice when we run it with QEMU, we have to specify where to find the cross-platform libraries, okay? But it runs the same way, and it's all good. This should work for you. If it does not work for you, let me know. What about assembly? Well, here is a greeting program in assembly, and this is set up for AMD. So don't worry about the content of it right now. We'll learn all this over the course of this semester. A short assembly style guide. Directives. Global is a directive. Labels, start and greet are labels. They'll start in column 0. Most other stuff will be indented. Instructions will be indented, and their operands will be indented. We insert blank lines just to divide up logical sections. That's my whole style guide for you. Do what you feel comfortable doing. Assembly is a line-oriented language, so just be aware of that. We can check that. So we put that in a file. We use NASM. We tell it we're compiling an ELF 64-bit, and we give it greetamd.asm. Then we link it using LD, which is the linker on the machine. We get the output, greetamd, and we do file, and then we run it, and it should just work. This should work for you. If it doesn't, let me know. What is linking? Some of you may be asking. We will cover linking in detail later in the class. All programs get linked. GCC may call it automatically for you. The assemblers will not. What about ARM? Here is that program in ARM. At least ARM Architecture 64. Again, there are directives. There are labels. They look a little different here because we're using a different assembler. Different assemblers have different ways of processing stuff. The instructions themselves look different because now we're on ARM as opposed to AMD, and so you see some different stuff there. And we'll go through how most of this stuff works. Don't worry too much about the content of it just right now. You may notice this file ends with a capital S. That's a common thing for GNU assembler. I don't know that I will follow this throughout the rest of the class. It doesn't matter. If you put a dash capital S, it'll assume it's assembly. If you put a dash ASM, it'll assume it's assembly. If you put a dash TXT, you can still feed it to the assembler, right? The extension doesn't matter that much, except for us. I'll try to use capital S for ARM assembly and ASM for AMD assembly, just so we can tell these apart. But I can't guarantee I'll always do that. And you'll have to. How do I assemble and link and run that? Again, I use the cross-platform stuff. So now instead of using NASM at the top, I use the cross-platform version of AS. So I type AArch, tab, and then I pick the AS option. I give it the file I want to assemble, and I tell it where I want the output to go. I use the linker, the cross-platform version of the linker, to link it. Then I can run a file on it, and now to run it, I do the same thing I did for the C program. I use QEMU, I give it the library path, and I run it, and I should get the output. If this does not work for you, let me know. Now, what about the Windows subsystem for Linux? I mentioned it before. People have had problems with it in the past. You can install it and try to use it, and that's fine. You'll install it out the Microsoft Store. You'll go find the Windows subsystem for Linux. You'll go find Ubuntu. So, for example, here in the Microsoft Store, I've searched up Ubuntu. I found it. At the time of writing, the most recent version available is 24.043, which is not the version we're using in this class. It's behind. I don't know how that will change by the time the class comes around, but for this class, we're planning to use Ubuntu 25. So, your mileage will absolutely vary. There are big changes between 24 and 25 that will affect the output of some of the programs that we use. I want us to be working on modern systems, modern processors, modern operating systems. I'm not going to hold back, just for the sake of examples or whatever. I want us to be on the modern stuff, and you should want that. Can you still cross-compile on the Windows subsystem for Linux? You can, but the same provisos apply. Let's do an example. Here's a program. Over on the right-hand side, we see hail1.c. This program has to do with the hailstone numbers, the collapse conjecture. Don't worry about that for now. It's an example I like to use in class. Just be aware there's some C code over there. It's standard C11. The thing that might be a little bit confusing to some of you is the uint32_t and the PRI-U32. If they are, you've had bad teachers for C. You should be using int_types.h, and you should be using the standard integer types defined by the C standard. For example, uint32_t is an unsigned 32-bit integer. You should know what those are. You should be using them. So we're going to do it. All right. When you run this code, it gets to that scanf line, and it waits for you to input a number. You input the number, it does some computation, and it writes out a result. So, for example, if you run it and input 17, it prints out 12. Okay, interesting. What does the program print for the input 19? How would you figure that out? I could stare at it, think about it really hard, or I could just type in 19, right? That's dynamic analysis, right? So I run the program, I put 19 in, it prints 20. Now I know, or I think I know, the answer. We'll get back to why you might not really know the answer in a bit, okay? But there we go. That's how I would answer that question. Is that reverse engineering? Posing a question about software and then finding a way to answer it? Yes. If you want to make it seem formal, call it dynamic analysis. What about this question? For what inputs, if in fact there are any, does the program print 0? How would you find that out? Well, I could run the program and keep running it and entering different numbers and see if I get a 0, but I might get a 0, and in which case I know maybe one input that yields a 0. Do I know them all? Maybe I never see a 0. And maybe then I don't know. Did that tell me that nothing gives a 0 or that nothing I've entered gives a 0? You can see the problem there, right? We might run it and try different values. Will we find them all? Will we find any? I don't know. All we know is the particular observation we've seen. Okay? So instead, let's read the code and see if we can figure out how to make the output 0. Well, we know immediately the output occurs down at that bottom line. There's the printf statement. Great, we got that. It prints count. Now we know something. Where does count come from? Well, count comes up here at the top, and it's initially set to 0. Great, that tells us that if nothing happens to count, we'll output 0. If something happens to it, maybe, maybe not. What happens to count along the way? Where is it modified between when it's set to 0 at the top and it's printed at the bottom? Only one place. Count is modified right there, and it's changed by incrementing it. So from 0, we can only go up. So we only go up, which means if I want to get a 0, I need that line to never run. When does that line run? That line runs whenever a number, the number we enter at the prompt, is greater than 1. So if, for example, I enter 1, that while loop will not run and count will still be 0. If I enter 0, that line will never run and count will still be 0. What are my choices for input? Well, it looks like, according to the scanf line, I'm using an unsigned 32-bit integer. That's what I'm giving you. So which unsigned 32-bit integers are less than or equal to 1? Well, there's just 2. There's just 0 and 1. That's it. So that tells me the answer to my question. Right? If I enter a 0, I get 0. If I enter a 1, I get 1. I can check it through dynamic analysis and verify the answer to the question that I got by static analysis. Great. Now I know something about the program. Powerful information, right? Is it true? What if I give it a negative value? The scanf line takes unsigned 32-bit integers, but what if I give it something negative? What if I give it something that's not even an integer? Well, hopefully it'll trigger an error condition, and I'll return -1. Is that what happens? No. When I run Hail1 and I enter -7, I get 317. That's not right. When I enter Fred, I get 0. So that my error checking for scanf isn't working. Why is that? Right? Shouldn't that work? Well, I go and as a last resort, I read the man page for scanf. I say, what is scanf supposed to do? And it tells me it returns the number of items successfully read. Oh. It returns an error when it reads it in the file. And that's the only time. Well, when I typed in Fred, that wasn't the end of file, but it didn't read a number from it, so it probably returned a 0. How can I see what it returns? Well, I'm going to modify the program to print out the value of number after scanf runs. So you see there, I still have that same line. I get retval to be whatever comes back from scanf after it reads a value in the number. And I check to see if retval is less than 0. If so, I'll return -1. And then I print out whatever's in retval. And I also print out the number. So I print out the number I got, and I print out the return value. So I'm going to see the number that was read by scanf and the return value that came back from scanf. So, great. I've made a change to the program based on my static analysis, and now I'm going to run it and use some dynamic analysis. When I do that, I enter -7, I get that ridiculous number, and it tells me, yep, I read 1. I read 1 unsigned 32-bit integer. What? I entered -7. Turns out -7 plus that number gives you the maximum value for 32 bits. That is the 2's complement version of that. And when you enter that number at the prompt, if you just ran Hail2 and entered that giant number, you'd get 317. Okay, fine. I guess that makes sense. What about entering Fred? When I enter Fred, it tells me the number was set to 0. I read 0 unsigned 32-bit integers, and I returned you 0. So for Fred, we get the 0 return, meaning he didn't read anything. And that's tricky. Right now we get a 0, but we could have gotten anything. Why? We left number uninitialized. And when I entered Fred, it didn't read anything, which meant number stayed whatever it was. In this case, it was 0, so I printed 0. Now, on older Ubuntus, so if you who are running Windows subsystem for Linux and installing an older Ubuntu can try this. On older ones, the C compiler didn't necessarily initialize stack variables for you. Memory gets initialized. Since the earliest versions of Linux, when I allocate anonymous memory, it gets initialized for security and safety and all that. But it turns out that this variable is an auto variable, which is allocated on the stack, number is, and I can have C build in initialization of auto variables. And by default, in the most modern Linuxes, that's turned on. But if it's not, I can get something else. I can get random values when I enter Fred. And you can see here, I've told it trivial auto variable initialization should be to a pattern and not to 0. And so when I do that, I get this ridiculous number, which gives me a strange output, right? Because Fred was never properly initialized. There you go. So we've learned quite a bit. We've learned that there are inputs we know about and outputs we see when I run a program. So I take a program, I run it. There's stuff I know about, like what I type, like Fred, and outputs we see, like the 0 or the other numbers. I see all of that. But there could also be inputs we don't know about, like the initial state of memory, right? If I compiled this on an older Linux, or I compiled it with pattern instead of automatic initialization, I would see something different. Well, I don't know the initial state of memory, I don't know the compiler options that were used. And if I don't know those, I won't necessarily be able to predict the outputs. That'll be an output I don't expect because there were inputs I didn't know about. And there can also be outputs we don't see. For example, a temporary file created somewhere, a signal sent back to some remote site. Tons of stuff can happen that we don't necessarily see. And that can all matter for dynamic analysis. When we run a program for dynamic analysis, we are conducting an experiment. I'm poking it, and I'm seeing how it pokes back. And I need to establish experimental control to the extent that I can. So I want the conditions to be controlled, right? There are controlled inputs, and there will always be uncontrolled inputs. I said always. Yeah, there will be, right? I don't know. Am I controlling the memory pressure? Am I controlling what other cores are doing? No. I'm running this in some context. And so just like an experiment where I survey people, or I pull fish out of a pond, or colored balls out of an urn, or any of that, there's uncontrolled variation that may creep in. And that's true even when I'm doing dynamic analysis, even for simple programs like this. So you need to understand what's observable, what are the observables, what are the controlled things, and what are the unobservables to the extent that you can. For static analysis, it's the same story, right? Except in this time, instead of running the program, I am building a model of the program, a mental model of it, or an actual model in some system. I'm building a model of it. And there are inputs I know about and outputs that we will see, and there are inputs we don't know about, which might lead to outputs we don't see, or any of that could be true. For example, if I'm statically analyzing the program, but I don't know which version of Linux you're running it on, I can't tell you what Fred's going to give you as the output. If I don't know the compilation flags, I can't tell you. And those are things I don't see when I look at the source. So again, for static analysis, we still need to consider cases where the system exhibits undefined behavior and understand that our static analysis is not always going to be powerful enough to let us see all of that. Full behavior of it? Well, let's say I enter a big number. What if I enter something that's not an unsigned integer, right? We know what it does in that case. We could fix the program to account for that. But what if I enter something that is out of the 32-bit unsigned integer range, right? The -7 got cast to an unsigned integer, so I saw the result, the 2's complement version of it. But what if I enter something outside the range entirely? Well, let's try that. So over on the right, I have entered the highest 32-bit integer plus 1. So this overflows the 32-bit range, and I get back 0. It thinks it read a 0, but it did read a number because I get back a 1. That's great. This leads me to conclude that what's happening is basically modular arithmetic, right? It's wrapping around at 2 to the 32. Is that true? So 64-bit integers have those values. And so I'll enter the maximum value for a 64-bit integer, and I get back the maximum value for a 32-bit integer, and that supports my hypothesis that it's mod 2 to the 32. So far, my hypothesis seems to be true based on the evidence I'm collecting by running my experiment. Let's try values around the maximum. So I go down by 1, right? And I go down by 1 on the number it reads. That supports my hypothesis. I go up by 1, so I'm entering the maximum 64-bit value plus 1, and what I get is the maximum 32-bit value. That means my hypothesis isn't true. So it seems like what it's doing is it's parsing up to a 64-bit integer and then maybe performing modular arithmetic after that. It's unclear. But we know it's not strictly mod 2 to the 32, or that result wouldn't be the way it is. So again, we can construct a hypothesis. We can base that on static analysis or even dynamic analysis, and we can use further static and dynamic analysis to try to test that hypothesis and see if it's true. We can always go and open up scanf on this platform, on this version of Linux, and take a look at its code, and that might tell us what's actually happening, and that would be true for this version of Linux and this version of scanf. So, reverse engineering is a process, and I think you saw that, right? We figured out how to answer those two questions, right? What does it give me when I put in 19? Does it ever produce 0? And then, how is it working, right? We figured those out by trying a combination of static and dynamic analysis. We ran examples. We used values around known limits, and that's very common. These are all the things that you will do to analyze programs, and what we're going to try to do is figure out how to automate this sort of analysis. Why? Why is this relevant? Vulnerabilities. Vulnerabilities in software tend to occur at the edges, and that can be when a limit is approached or met or exceeded, or it can be where two systems connect and share information. That's commonly where you're going to find vulnerabilities. So, here's an exercise, not homework. It's not a homework. It's just a little exercise for you to do. I want you to log into the virtual machine for the class. That's going to cause your account to be created. Please do that because this is a two-step process at the time I'm recording this lecture. Please log in and do that so your account gets created. Once you're notified that it's created and you're ready, go ahead, log into your virtual machine and go through the exercises in the configuration section, and then be sure that you can do all the little things that are there. You can compile the program for AMD64 and AArch64. You can do the assembly stuff and run it, make sure all of that works. That's it.